Uh, Now in module 4.2, we'll try to solve the same problem, multivariable optimization with equality constraint, but we'll use something new called Lagrange multiplier. So let's see what does this mean. Here is Lagrange, as you can see, he's very thoughtful. And Lagrange multiplier is really showing you, or should show you, why Lagrange was one of the smartest people ever alive, without exaggeration. And some of you may be aware of it if you have taken dynamics or from other fields. The method is fairly universal and applied to many fields. Okay. So again, we are minimizing fx subject to gjx. X has n variable, and I have j constraints. And it makes sense, of course, from what we discussed before that m should be less than n. So we would like to solve the problem without doing this incorporation of constraints into the variable, replacing x2 by x1. So how we'll do this? So basically what Lagrange proposed is to increase the number of variables by lambda, where lambda will be the number of these variable equality constraints. So my function now is L of x comma lambda. So I increased my variable by, like assume that you have 3 equality constraints, so you have 3 more variables. And I didn't want to call them x to avoid messing up things. Is fx my original function plus sigma j equal 1 to m lambda j gjx. And we can see that how we will use this. So, but anyway, for something like this, I still need a first derivative to disappear for L, which is my function. And let's see what will happen. Here is example, same example we had before. X1 squared plus x2 squared is my function. And I have constraint x1 plus x2 minus 5 equals 0. One variable, one constraint, so I'm adding one variable, lambda 1. And here is my new function, the original, plus lambda 1 by x1 plus x2 minus 5. And when I differentiate, partial differentiation, I get 2x1 plus lambda, 2x2 plus lambda. Then my last one will be basically the constraint. So this clever representation will basically add your constraint as d by dl by d lambda 1, lambda 2, lambda 3. And all of these has to be 0. So basically, in my formulation, I'm automatically satisfying the equality constraint. So how to solve this? I have 3 unknowns, x1, x2, x3, sorry, lambda 1, and I have 3 equations. So I will go to first and second equation. We'll say x1 and x2 in terms of lambda. So if I substitute this in the third equation, I will put minus lambda 1 over 2 minus lambda 1 over 2 plus 5 minus 5. So you will get lambda 1 equal minus 5. So what is the meaning of this? Basically, this variable is telling you how you can make x1 and x2 correspond to a minimum point while satisfying the equality constraint in the same time. So of course, when I substitute minus 5, it would be minus minus plus 5 over 2, 2.5, like what we did before. So it's really interesting to look at what we are doing graphically. Here is the contour plots again. And at this point, the two slopes cancel each other. The slope coming from not the slopes really, the component of the slope coming from here and here. And this is why This point is a minimum point.